So in example 1 here again, we're going to be seeing 3 different ways that we can determine whether a sequence is increasing or decreasing. We're going to use this particular sequence, n over n plus 1, and show that it is strictly increasing using each of these different techniques over the next 3 videos. Now, the reason again that this is going to require more than just writing out some of the terms of the sequence is that these definitions up above required that these increasing or decreasing properties would be true for the entirety of the sequence. And since this sequence never stops, I have to do more than just write out 5, 6 of the terms and go, oh yeah, they go up, or oh yeah, they go down. I have to see more than that. So let's take a look at the first of our 3 approaches. Our first approach is going to be a calculus approach. And I need to be able to spell there, but let's see. Calculus approach. Okay, so if I'm working with a calculus approach, I'm going to go back and start to focus on a matching function for this particular sequence. So I'll say, let's let f of x be equal to x over x plus 1. Remember that we saw in the last section that if I have a function f of x and my sequence just corresponds to kind of dots along that function, then I could probably say that if my function tends to be increasing on a given interval, then my sequence is increasing on that same interval. So I want to go ahead and determine if my f of x function is increasing or decreasing and where that happens. Of course, to determine that, we would calculate a derivative. So I'll see here that we calculate f prime of x is equal to, and I'm going to have to use the quotient rule here. So let's see. I'm going to have my x plus 1 all squared, and then my x plus 1. Remember that then I can go ahead and the rest of the numerator is going to kind of act like a product rule, but just with a subtraction. So I've left the x plus 1 alone. Now I'm going to do derivative of x, and then subtract and reverse the order. Notice that when I do this, though, I still am going to have an x on top with a negative x that are going to cancel out, and I'm going to be left with 1 over an x plus 1 all squared. Now, if I was in a Calc 1 class and trying to find where this function increased and decreased, I would attempt to find some critical points, right? So I would have to say that f prime of x is equal to 0. Well, wait a minute. Can this thing ever be equal to 0? No, it can't. So I'll just say this is never equal to 0. However, I would also need to find when this thing is going to be undefined. So I can say this is undefined when x is equal to negative 1. These are my critical points. So now I can go ahead over here. I could imagine drawing out a little number line of x's. And on here, I'm going to go ahead and say that when I go to negative 1 for x, and I calculate what the derivative is, I get undefined. I can now pick other values of x on either side to kind of test what happens in the derivative. Notice that if I go here and I plug in a number like positive 5, I'm going to get a positive result back out of the derivative. But I actually get the exact same thing if I plug in something like a negative 5, because this square is making everything ultimately positive. So I can see that my function f of x is increasing from negative infinity to negative 1, and then from negative 1 to positive infinity. It's not increasing at negative 1, since it's undefined there. However, I'm going to go ahead and note that I don't really care if f of x is increasing, like on negative values. I only care if it's increasing from where that first dot is going to be starting, which I know starts at n is 1, or x is 1. So really in here, I'm curious about what happens once I get past the value of 1. However, since my function is increasing from negative 1 to infinity, I could definitely write the following. I could say f of x is strictly increasing, right? Notice it's only getting larger. It never hits 0 and like bottoms out again and has a horizontal tangent. It only goes up. This is strictly increasing on the interval 1 to infinity. Now it's increasing strictly in a bunch of other places, right? From negative 1 to positive 1, from negative infinity to negative 1, but I don't really care about those. because I just care about this interval, because I know if the function's increasing here, then a sub n is strictly increasing on this interval 1 to infinity. Therefore, I have that a sub n is strictly increasing, and my argument's complete. So this is one possible approach. But you could start to imagine that there might be times where taking a derivative of a matching function could be a bit complicated. Maybe this isn't always the most optimal approach. And so in the next couple of videos, we'll look at some alternative approaches that we can take.